Hi everyone, welcome back to another Pre-Calculus 12 video. I am going over rational functions today. I'm going to give you a brief summary of section 4.3 from your workbook. So I'm going to attempt to summarize the notes that I've already sent out to you and give you a condensed, shorter form. So we'll start off first by just talking about what rational functions are. So in its most basic form, let's say we had f of x equals 1 over x. That would be the equation of a rational function. If we want to quickly sketch out or look at what the graph looks like, we know that this is the pattern that it takes. It looks sort of like this. And the biggest thing, oh, that's an awful looking graph, but just pretend it's wonderful. There we go. The biggest thing about this is if we look this way, you could see, or we would make the assumption that those arrows are getting closer and closer to that line, but not quite touching that line, the y-axis. So this we would call a vertical asymptote. You're familiar with this from last year, so I'm not going to spend too much time on that. That would be at your x equals 0 or your y-axis. And here the same thing would be happening with the x values, where from the top and bottom it would be approaching the x-axis, and in this case that would be a horizontal asymptote. So that's the thing with our rational functions. You'll be dealing with vertical and horizontal asymptotes, and sometimes you'll even have a hole in the graph. So we are going to focus on the algebra and the equations and what it looks like. And if you're interested, section 4.4, which we're not going to do, but it would be on graphing these rational functions. So what I'm going to suggest is when I give you an equation today to work on, the algebra, you are welcome to take that, plug it into your graphing calculator or into Desmos. I'll write that out for you if you don't know this already. Desmos is an app that you can get online, or you can just go to the website, and it basically is like an online graphing calculator. So you can punch in the equation and it'll spit out what the graph looks like, so you can sort of connect the graph to the algebra, which is the part we're going to focus on today. So there's your quick introduction. Let's get into some quick examples. Let's say we have, for example, f of x equals x over x squared minus 16. So for this first example, all that we're going to focus on is the vertical asymptotes to start off with. So we're going to analyze this equation. You get to see why we practiced or you learned all these skills over the years. You learned how to factor so you could take stuff like this and break it down. So for example, we would want to look at the bottom and notice it's a difference of squares. So we can factor this to be x plus 4, x minus 4 at the bottom. And that's how we find our vertical asymptote, is we analyze the bottom, like whatever you're not allowed to have at the bottom. So in this case, if we're analyzing that one, I know x is not allowed to be negative 4, because if I plug in negative 4, I get a 0 in the denominator. That's not allowed. And from this one, x is not allowed to be positive 4. For the same reason, if I plug in 4, I'm going to get 0 at the bottom, and that's not allowed. So to show you what's happening, what that means is on our graph, we would have a vertical asymptote at, I'm just going to say that's negative 4, and I'm going to say that is positive 4. So this is how the algebra translates to the actual graph. So getting a 0 in the denominator is not allowed. So whichever number or restriction you have in the denominator, that's what tells us where the vertical asymptote is at. So I don't want to write out vertical asymptote over and over again. I'm okay with you doing this as well. We can shorten it and say vertical asymptote at x equals plus and minus 4. That's how I would give my answer or my result in this case. Since we're looking at this right now, I'm also going to talk a little bit about analyzing this equation to get the horizontal asymptote from this as well, which I'm going to abbreviate like this, so I don't have to keep writing it over and over again. But basically, in order to determine if something has a horizontal asymptote, we analyze the degree of the top of the equation compared to the degree of the bottom of the equation. So in this case, since the numerator degree is less than the denominator, oh my gosh, I don't know why I can't spell this right now. I'm just going to do this. The denominator degree, there is a horizontal asymptote at this point here where y is equal to 0. That's a rule. So this is something, I'm going to highlight this. This is a rule that I need you to know. We have a horizontal asymptote at y equals 0, which on the graph would mean we'd have, oh gosh, this is not turning out very pretty, but you get the idea. Right on the x-axis, also known as y equals 0, that means that we would have a horizontal asymptote there. Okay, so that's basically a summary of this whole section. But I get that you're probably thinking, what? That's not enough, I don't get it. So I'm going to give you another one. Let's say, for example, we have g of x equals x plus 5 over x cubed minus 9x squared. We're still doing exactly the same thing. So compare it to the last equation. It's just this time I have more stuff going on in this function g of x. But I still do the same thing. I take the same approach, which is I want to, maybe I'll just do it over here. I have my x plus 5 at the top, but at the bottom I want to factor this out. So I analyze this and I see that I can just factor out an x squared, and that leaves me with x minus 9 inside the brackets. So that tells me, if I look at this, x is not allowed to be 0, because if I plug in 0, that gives me 0 in the denominator. And here, x is not allowed to be equal to 9. So these are the restrictions. I'll write that here, restrictions. And how that translates into our answer is that there's a vertical asymptote at x equals 0, and another one at x equals 9, because both of those things are not allowed. So that's a quick summary on how we find the vertical asymptote from our equation. Basically, take a look at both of these examples. They're so bright and colorful, I love them. Take a look at the bottom, factor out the bottom, decide what's not allowed or find the restrictions. From that, you pull out what the vertical asymptote would be. Whatever is not allowed, that would be the line or the equation of the line that is your vertical asymptote. Okay, I talked a little bit about the horizontal asymptotes. Let's focus a bit more on that. I'm going to give you just some very specific examples. Horizontal asymptotes. Just so that I can clarify and zoom in specifically on the horizontal asymptote without worrying about the vertical asymptote. So I did go over it in the first one, but I'm going to give you some just to focus on this. If I have f of x equals -4 over x plus 4. Remember what I told you in the first example. If I analyze the degree of the top compared to the degree of the bottom. Notice that there is no degree at the top, it would be 0. There's no x there. And at the bottom, there is an x. So that tells me I have a horizontal asymptote at y equals 0. Just like that first example that I went through with you. Okay, so there's different types of horizontal asymptotes that can show up. It's not always at y equals 0. So let's take a look at something that's a little bit different. So here's this new function g of x, and it's 2x over 3x plus 5. In this case, the degree of the top is the same as the degree of the bottom here. I have an x to the 1 at the top and the bottom. So, I don't like that, I'm going to get rid of it. So because I have an x to the 1 there and x to the 1 there, this time my horizontal asymptote is the ratio of the lead coefficient at the top and the bottom. What am I saying? Lead coefficient would be the 2 in front of the x at the top and the 3 in front of the x at the bottom. So my horizontal asymptote is the ratio of the lead coefficient, so it's 2 over 3. It's at y equals 2 over 3. You can see this isn't quite as neat and tidy as a whole number, so this isn't quite as common, you won't see it as much, but we need to know this. So this is where your horizontal asymptote shows up, only because the degree of the top and the bottom is exactly the same. When that's the case, we take the coefficient of the top and we take the coefficient of the bottom and we create a fraction or a ratio based on those two. Okay, so if instead I had h of x is 3 minus 2x over x squared minus 5x plus 6, if I want to get my horizontal asymptote here, okay, let's analyze the degree of the top and the degree of the bottom. The degree of the top is x to the 1. The degree of the bottom is x squared, so the one at the bottom is larger, so it's at y equals 0, just like in this first case here. So I wanted to show you this first example compared to this third one because it shows up in a slightly different form, but you end up getting the same asymptote. Okay, and then there's this scenario. Let's say we have f of x equals 3x squared minus 2x plus 1, and that's all over x plus 2. Let's analyze the degree of the top and the bottom. So in this case, at the top, it's x squared, and at the bottom, it's x. When that's the case, when the degree of the top is bigger than the bottom, there is no horizontal asymptote at all. So these are the different scenarios that can show up. There's one of 3 things that can happen. You can have an asymptote at y equals 0. You can have one at the ratio of the numerator divided by the denominator if the degree is the same top and bottom. Or you could have none at all if the degree of the top is larger than the degree of the bottom. Okay. And so the only other thing that I'm going to say about this is you'll get some questions in your workbook today where it asks you to find the vertical asymptote, the horizontal asymptote, we just went through that, and it's also going to ask you for the x and y intercept. That you've done in the past, I'm not going to go through that in this video, but I am going to very quickly talk about it. Let's say for this example here, I wanted to find the x-intercept. The x-intercept, we write it here, the x-intercept is where y equals 0. All I would do is throw in a 0 here, and then multiply that by x plus 2, so that would get rid of that. And then I would solve this in order to figure out what the x values are at y equals 0. And that's how I would find my x-intercept. To find my y-intercept, it's the opposite. I would plug in x equals 0. So in this equation, I'd throw in a 0 there, throw in a 0 there, throw in a 0 there. Yes, I'm being lazy, but I want to keep the video short, and this is based on stuff you've done before. So notice that that would wipe this out, wipe this out, wipe this out, and I would solve to find my answer for my y-intercept by working my way through that. I would do the algebra, top and bottom, and I would find that it would be equal to 1 over 2. So that would be my y-intercept. Okay, so that also I don't really like. I'm going to get rid of it. But there's a quick, brief summary on how you would find that. And then one last thing I want to show you, which is how to find a hole when you're dealing with rational functions. Rational functions, just to show you or remind you, is basically just a polynomial in the numerator over a polynomial in the denominator. So it's not a bunch of separate stuff that we're doing. We just are taking the polynomials chapter and now we're sticking them into a fraction. So it's really not anything new. It's just a new concept that's building on what you've already done. Okay, so in order to look at how a whole shows up in a graph, let's take a look at a function that looks like this. Let's say we have f of x equals x squared minus 9 over x minus 3. Okay, so if I want to look at a function like this, I'm going to take, like, let's say we were looking at the horizontal asymptote, vertical asymptote, or any of that stuff. The first thing we always want to do is start by factoring. So at the top, I know that that's a difference of squares, so it's x plus 3 and x minus 3. And we had an x minus 3 at the bottom already. When we see that, we can start to cancel things out and simplify. We always want to do that. So after doing that, all I'm left with is x plus 3, which is just a linear function. But guess what impact this part has? The fact that we cross this out tells us that we have a whole at x equals 3. We have a whole at x equals 3, but we want to figure out the precise point. So that gives me the x value of my point. I want to plug this into f of x equals x plus 3 to figure out what the y value would be. So I can say f of x, no, I should say f of 3 from this 3 here, equals 3 plus 3, which is equal to 6. So I have a whole at the point, and I always want you to give this as a point, 3, 6. So that tells me where the whole is. Because this just worked out to be a linear equation, there are no asymptotes. But if I were to go and quickly sketch this out, I'm just going to do a really rough sketch of what this would look like. We know that this is just a linear equation. I'm just going to say that's plus 3, that's where it goes through, and then up 1 over 1, the slope would be 1. But when I get to the point where it's at 3, 6, so I'm just going to make it up. Let's say it's there. And I'm going to make that up and say that that's 6. At that point, I'd have a hole there. So it would be a line that goes like this, but at the point 3, 6, it would leave a hole in my graph. So that shows you how this looks graphically, or the impact that it has when we can cancel out factors at the top and the bottom. Okay. That's it for today's work. And basically for section 4.3, as I promised, I am giving you a condensed, sort of like a Coles Notes version of your math lessons while you're doing them online. So you're going to be doing numbers 3 and 4 in your book. I am going to say you can do the odd letters, so to remind you, that means you can do A, C, E, etc. But use your judgment. If you're struggling to understand this stuff, don't just do the odd letters, do all of them. So do more to practice until you get the hang of it. And similarly, if you've done a few and you've completely got it and you're good with it, then you decide how many you're going to do. But that's the suggested work. And just to remind you, 4.4 would have been graphing rational functions. I want you to, again, go to Desmos online or get the app and plug in all of the equations that you're doing today. This is a part of your homework. Use Desmos to look plot the graphs that you're doing in numbers 3 and 4. And we're going to say that that takes care of 4.4 for you. Okay, so I hope that that was helpful, and that's the end of chapter 4.